Welcome to Tennessee's at-home learning series for math. Today's lesson is for all our 8th graders out there, though all students are welcome to tune in. Today's lesson is the 13th in our series. My name is Candace Thompson, and I'm an 8th grade math teacher at Oakland Middle School in the Rutherford County School System. I'm so excited to be your teacher for this lesson today. Welcome to my virtual classroom. If you didn't see our previous lesson, you can find it on the Tennessee Department of Education's website that I have pulled up here. If you will scroll down to Math Grade 8 and click on Student Packet, that will have our worksheets that you can complete at the conclusion of our lessons. Today we'll be learning about systems of linear equations, and we'll be working on estimating solutions for or by inspection. Before we get started, to participate fully in our lesson today, you will need paper, pencil, and a hard surface to write on. A calculator is not required, but it may be used to check your calculations. Okay, let's begin. So you may recall that in lessons 11 and 12, we used this chart here, and this shows us the maximum heart rates based on a person's age. Remember that X represents the age of a person and Y represents the maximum heart rate. Here's what we wrote in lessons 11 and 12. Our equation was y equals 220 minus x. Remember that x represents the age of a person and y represents the maximum heart rate. Let's work on another problem to do the same chart. Give two ordered pairs that are solutions to the equation. How can you find an ordered pair that is a solution to the equation? You can pick a value for x, substitute it in the equation, and solve for y. The heart rate that is 80% of the maximum heart rate of a person who is 20 years old is 160 beats per minute. The heart rate that is 80% of the maximum heart rate of a person who is 40 years old is 144 beats per minute. Therefore, the ordered pairs are 20, 160, and 40, 144. How does this information in the table help us to interpret the meaning of the equation and the ordered pairs? The table shows that 80% of the maximum heart rate, which is 220 minus the person's age. So the ordered pairs give 80% of the maximum heart rate, or a vigorous exercise maximum heart rate, for two specific ages. There are many ways a function can be represented, such as tables, graphs, and descriptions. Let's look at some other problems. Are you ready? Okay, let's get started. Using substitution to solve a system of equations is a useful method when it is easy to isolate one variable in one or both of the equations. For instance, listen to this problem. Gemma sells tickets at a local fair. Adults are $13.50 each, while children's tickets are $7.50 each. On Saturday, she sells 800 tickets and collects a total of $7,680. How can Gemma determine the number of each type of ticket that was sold on Saturday? Now that we've heard the problem, get out your paper and pencil and let's write a system of linear equations to represent the situation. We know that the number of children's tickets plus the number of adult tickets equals the total tickets. If C equals the amount collected for children's tickets and A equals the amount collected for adult tickets, then our system of equations would look like this. So we know that children's tickets plus adult tickets, the total when they were added together, there were 800 tickets sold. So that's where we come up with that first equation. So first, we're going to solve one of the equations for one variable. If you can follow along and solve for C yourself, great. Here's what we have to do when we solve for C. So we want to use this first equation and set C equal to something. So in order to do that, I'm just going to move A over. So I have that C is equal to 800 minus A. You can substitute 800 minus A for C in this other equation. Then solve. Try writing this with me. So we will plug in, let's see here. So we will plug this in for where we see the variable C, and we'll solve. So we have 750 times 800 minus A plus 1350 times A equals 7,680. So now we're going to simplify, and we get 6,000 minus 750A plus 1350A equals 7,680. We're going to combine like terms, so we get 6A. We're going to combine like terms, and then I'll move this over all in one step. So I get 6A equals 1,680. After dividing by 6, I get that A is equal to 280. From this, we know that there were 280 adult tickets sold. Now, let's solve for the other variable. You can substitute 280 for A in either equation where you see A and solve for C. So I could plug in 280 in this equation for A or this equation for A. I typically choose the smaller equation, the one that's the least amount of work, so I can get my work done quickly. So I'm going to use this equation here. So I'm going to rewrite C plus A equals 800. So C plus 280 equals 800. And using this, I know that C is equal to 520. So now we can determine that there were 520 children's tickets sold and 280 adult tickets sold on Saturday. What if you wanted to substitute the value for A in terms of C in the equation? What value for A would you use? That's right. You would simply solve C plus A equals 800 for A. Instead, to get A equals 800, A equals 800 minus C, and we would come up with that same answer. Let's look at another problem. Listen to all the information first, then get that pencil and paper ready. Andreas takes pottery class at 2 different studios. At the community pottery studio, the cost is $14 per hour with the cost of clay included. At the private pottery studio, the cost is $28 per hour plus $15 for clay. Is there a number of hours for which Andreas's cost is the same at both studios? So now we'll write our system of linear equations together. Let x equal the number of hours and y equal Andreas's cost. And we come up with y equals 14x to represent the community pottery studio because the cost is $14 per hour. And then y equals 1/2 times 28x plus 15 and that would represent the cost at the private pottery studio. Since both equations are set equal to y, what would you do first? That's right. You would set up an equation using the 2 expressions that are equal to y. We can use the substitution to solve one of the equations for one variable. So I know that y is equal to 14x. So where I see y in the second equation, I'm just going to put 14x in that place. So I have 14x equals 1/2 x, or 1/2 times 28x plus 15. I'm going to go ahead and simplify this side and just multiply both of these terms by 1/2. So I have 14x equals 14x plus 750. I'm going to subtract 14x over here, and I'm left with 0 equals 750, which is not a true statement. So since this result is not a true statement, the system has no solution. There is no number of hours for which Andreas's cost is the same at both studios. If we look back, there are some clues that this will be a false statement. For instance, if you recall earlier lessons on slope-intercept, the slopes for this problem would be the same, but the y-intercepts are different. All we'd have to do is just distribute this half. So when we do that, we end up getting y equals half of 28 is 14, and then half of 15 is 750. And you notice they have the same slope. So remember, we talked about in earlier lessons, if the slopes are the same, but the y-intercepts are different, the two lines made from these equations would be parallel. Now let's try a different type of problem. I'd like you to follow along and try to write out as much of these as you can. Take a look at this system and solve by using substitution. Okay. Let's use substitution for now to solve the problem. We're going to substitute. Well, first thing that we need to do is we need to set one of the variables equal to something. So if I use this first equation, I can easily just set the variable x equal to something. And I'm going to do that by moving 2y over. So since 2y is negative, I'm going to move it over by adding it. So I have negative x equals 2y minus 8491. I've got to get rid of that negative 1 coefficient here. So I'm going to divide each term by negative 1. And that's going to end up just changing the sign of each term to its opposite. So I have that x equals negative 2y, and then that would make that a positive 8491. Okay, so now that I have that x is set equal to something, I'm going to plug this in where I see x in this second equation. It's really important that when you plug it in, that you plug everything in correctly as you see it. So I have 3 times x, but instead of x, I'm going to plug this in. So negative 2y plus 8491 plus 6y equals 254.73. So now we're going to do a little work by simplifying. So I have I have negative 6y plus 254.73 plus 6y equals 254.73. So I'm going to combine these two, and when I do, they're just going to cancel each other out. So I'm left with 254.73 is equal to 254.73. So the result is a true statement. This system has infinitely many solutions. What happened as a result of substitution in step 2? The result was a true numerical statement with no variables, as you can see here. A system with an infinite number of solutions is made up of equivalent equations. We can see that this is true in the example because you multiply the first equation by negative 3. If you multiply this first equation by negative 3, then both, if I multiply all of these terms by negative 3, then both equations are equal to 3x plus 6y equals 254.73. So you can see that they end up being equal to the same exact thing here. All right, let's look at another problem. Okay, so Brandon took a 50-question exam worth a total of 160 points. How many of each type of question were on the exam? Based on this information, what should our system of equations look like? Well, we've already determined that x is the 2-point questions and y is the 5-point question. So it should look something like this. I know that the 2-point questions, which are represented by x, and the 5-point questions, which are represented by y, when I add them together, I had 50 questions in total. Now let's solve for one of the variables. So I am going to set this equation with a variable equal to something, and I can do that pretty easily for this one. So I can do that by simply moving this variable x over. So now I have that y is equal to 50 minus x. Did you get that same answer? Let's continue. We can substitute for y given the following. So now that I know that y is equal to 50 minus x, I'm going to plug that in where I see y in the second equation. So it would look like this. We have 2x plus 5 times what y is equal to, which is 50 minus x, equals 160. So I'm going to simplify that and get 2x plus 250 minus 5x equals 160. Going to combine like terms, and I'm going to move 250 over all in the same step just for the sake of time. So I'm left with x equals 30. Now we see that there are 30 2-point questions. With this information, we can solve for y. So I have what x is equal to. Let me use a different color here. So I know that x is equal to 30. So I'm going to pick one of these two equations. I'm going to plug in that value for x. I try to just always pick the more simpler or the more simple equation. So I'm going to pick this top equation. And I know that 30 plus a number is equal to 50, meaning that y is equal to 20. So would the problem have the same solution if you first, and so I isolated y first, would it have the same solution if I isolated x first? That's right, it would, because the solution is the same either way. So our solution, if we were to write it as an ordered pair, we would write 30, 20. But if we want to just put it in context, we would say that there are 30 2-point problem or 2-point questions and 20 5-point questions. Okay, let's look through a few more and you work along with me. All right, so we have this next problem. Let's get that up here. Okay. Amy and Mabel are taking a trip this summer. Together, they have saved $490 for their trip. Amy has saved $54 more than Mabel. How much has each person saved? So we're going to start by writing a system of linear equations. So we know that together, Amy and Mabel have $490 saved. And we also know that Amy has saved $54 more than Mabel. So her total is going to be equal to Mabel's total plus 54. So there's our system of equations. So now if we use substitution to find the value of m, it would look something like this. So I know that a is equal to m plus 54. So where I see that in the first equation, I'm going to plug that in. So guys, you're always just looking for one of the equations in my system to have a variable isolated. In other words, you're looking for an equation to have one of my variables set equal to something. If you don't see that that's possible, then you can rewrite the equation so that it does have a variable set equal to something. So I'm going to plug this term into, or I'm going to plug this in for A. And so this is what my equation would look like. M plus 54 plus M equals 490. So when I combine like terms and divide, I get m equal to 218. So now that we have m, we can substitute that in to find the value of a. So I know that a is equal to m plus 54. So I will just write that a is equal to 218, which I found for m, plus 54. So a is equal to 272. So what this means is that Amy has saved $272 while Mabel has saved $218. Now, here's one more for you to try mostly on your own. If you have a calculator and want to use it to check your work, that is okay. All right, here we go. A parking lot charges $7 per day to park on weekdays and $12 per day on weekends. Jamal parked his car in this lot for 6 days last week and spent a total of $52. How many weekends and weekend days did Jamal park? Here I've got a system of equations where x is going to be equal to the number of weekdays and y is going to be equal to the number of weekend days. Can you fill in the blanks? Write this on your own paper and finish it. So x plus y is equal to blank, and then blank x plus blank y is equal to 52. So let's fill in the blanks. So we know that x, which represents the days that we parked on weekdays, plus y, which represents the weekend days, we know that there was a total of 6 days. And then x is going to represent the number of days, and we know that it was $7 per weekday to park. And y is going to represent the weekend days, and so we know that it's $12 per weekend day to park. So now that we have our system of equations created, we need to isolate one of our variables. That is, we need to set one of our variables equal to an expression so we can use substitution. So I'm going to choose this first one here. And I have x plus y equals 6. I'm going to move x over. So I have y equals 6 minus x. And so I've achieved what I need to so that we can use substitution. I know that y is equal to 6 minus x. So I'm going to plug 6 minus x in where I see y in that second equation. See if you can complete it. So it should look something like this. 7x plus 12 times 6 minus x equals 52. And then once we solve for x, what did you find for the value of x? That's right. We found that x is equal to 4. How can you find the value of y? What's the value of y? If you said that you can substitute it into our original equation that we transformed here, so we would do y equals 6 minus 4, and then we have that y equals 2. Then you are correct. You are great at doing this. Okay, here's one for you to do mostly on your own. All right. Krista bought 24 notebooks and spent $104. The large notebook cost $6 each, and the small notebooks cost $2 each. How many of each type of notebook did she buy? Let's say that L represents the large student notebooks and S represents the small student notebooks. Now let's set up your equation. Did you set your equation up like this? We know that the large student notebooks plus the small student notebooks is equal to 24 because we bought 24 in all. We know that the large notebooks cost $6 each. And we know that the small notebooks cost $2 each. And that we spent a total of $104. Great. So how many of each type of notebook did she buy? So if you got that she has 14 large notebooks and 10 small notebooks, then you are correct. Great job. So you guys are really getting the hang of this. We're going to do some independent practice now. Just a reminder, if you will go down to grade 8 to the student packet, that is where all of our independent practice is. So good luck on that and great job today. I enjoyed solving systems of linear equations using substitution with you guys today. Thank you so much for inviting me into your home. I look forward to seeing you in our next lesson in Tennessee's At Home Learning series. Goodbye.